Yeah, let's get started. My name is Henning Horst, Director of R&D for Comforte, and today I would like to talk about the X9 tokenization standard, which has been released recently in August this year, and how that standard can help you achieve compliance and improve your security. So let's start with the basics. Basically, for the non-US folks, I'm not sure if we have any of those. Basically, the Accredited Standards Committee X9 is a ANSI accredited committee for developing standards in the financial industry, and this X9 119 is basically the code for the protection of sensitive payment card data. And that contains of two parts. One is protection using encryption methods, and the other one being using tokenization. And that was released in August, as I said, 11th of August this year. And this X9 119 Part 2, like a handy name, took about 5 years to be developed. And the thing that is being replaced by a token is called a USB, underlying sensitive value. So it can be a credit card number, can be a name, date of birth, whatever. So Comforte joined the X9 committee in April 2013. I was one of the three editors of the standard, of course, working with the broader group of various financial institutions to develop that standard. So there was, from the editors, that was Steve Schmaltz from RSA, and then Terence Spies, the former CTO of Voltage, and myself as the editors, splitting up the main body and then the sections that I'll be covering. So meanwhile, the standard can be purchased, $60. You can go to their web store and download that from there. So what's in the document? So if we look at the main body of the document, this is the outline. It starts with scope, what it does, what it doesn't do, normative references, terms and definitions, symbols and abbreviated terms like the normal stuff you would expect, and then it's really starting to become interesting. Defining sensitive payment card data elements is kind of the pre-step then to going a bit more into detail in the tokens, their attributes and their utility, and after that tokenization systems, component and system requirements. And the last part I skipped for this session, so we'll talk about the green parts here today, as I think those are the most interesting ones. And then there are annexes as well to the document. We'll talk about the acceptable tokenization techniques. That's one annex. Then there's another annex for static table-driven tokenization techniques and reference schemes. And then there's token use cases and guidance for tokenization. So let's start with the section 6 of the document, which is tokens, their attributes and utility. And it's really, if people talk about tokenization, it's easily becomes a miscommunication, in the sense of everyone understands something different when you talk about tokenization and tokens, and what's high value, what's low value, and where's the difference there. So the section 6 talks about the token attributes, which is basically those attributes that the token, thus the replacement value for this underlying sensitive value, shares with that original value. So for instance, the length of the value. So that's a typical thing for tokenization. Okay, you tokenize a credit card number, 16-digit credit card number, and the resulting token is also the length of 16, which makes it very easy to use in existing database schemes or message formats where you really need to keep the length of the data element the same. So then let's look at the token utility. So the full name of the standard is post-authorization and implementing post-authorization tokenization system. So what's post-authorization in this case? Basically, what we talk about is token utility. And what the excerpt here says, tokens have utility, which means they're useful in some context, and tokens are often spoken as of having value, labeled as high value or low value. And basically, the key here is a post-authorization token cannot be used to initialize a payment transaction. That's the key here. It doesn't matter when it is generated or when the actual tokenization happens, but the key is what do you do with that token. And that's the key here. What we typically talk about is security tokenization. So removing the complete utility of the underlying sensitive value. So if someone steals it, you cannot do anything with it. So that's in contrast to payment tokenization, where you can use the token for certain purposes, and it does still have some value in a restricted environment, more restricted environment than a typical credit card, but it still has some value for certain authorization operations. So we talk here about low value or security tokenization, which means low token utility, as opposed to high token utility would be EMV code tokenization or Apple Pay. So these Samsung Pay, those types of tokenization systems. That standard here, what we talk about, security tokenization. So I touched on this already now a bit. So if we look at the token, the attributes and utility, you basically see, okay, you can split it up by use, that's the utility, and then by format, that's the attributes. As said here, two different pieces, high value, low value tokenization. That's common terms, or security versus payment tokenization, or like the standard puts it, post-authorization token versus pre-authorization token. All the same thing, and hopefully this helps a bit to clarify when you talk to some other person, what the heck are they talking about when they talk about tokenization. And then there's the formats. Basically, that's the attributes. So is the token distinguishable from a pen? Is it an alphanumeric token? You can preserve certain characters in the tokenization operation. So that's all what's being addressed with those attributes. So let's look at the section 7, which is really the meat of the tokenization standard, if you will. And it talks about tokenization systems, components, and security requirements. And if we look at this, what we want to talk about is basically the first two sections, the tokenization system model and risk vectors for the tokenization system. So let's look at the tokenization system model. And basically what the standard identifies here and illustrates is splitting the various components that you have in your tokenization system. So it starts with the requesting entity, which can be either like a device or a human interaction, going to the token request interface, which then on behalf of that requesting entity requests the tokenization services. And of course, those tokenization services, there's the key that only those entities get access to the tokenization services that are actually allowed to and eligible to those tokenization services. And then the actual tokenization service contains the tokenization technique, which in itself then contains of typically two things, and we go into a bit of detail in there, namely the tokenization secret and the random mapper. So there are various ways of doing tokenization. And you can abstract them basically in this model. There's always some kind of a tokenization secret, and there's kind of a algorithm, a function, some kind of a mapping that actually does the translation back and forth from the sensitive data element to the token and vice versa. So, and where then the tokenization standard goes into a bit more detail, and that's, I think, pretty helpful for you also when you implement a tokenization system, looking at the security risks that go with it, respectively, knowing where to look and seeing, okay, where do you have to focus your attention in order to ensure that your tokenization system is running in a secure environment. That's, of course, part of it is the tokenization provider, so the vendor of the tokenization system, but there are certainly parts where you can configure the most secure product in a way that it's totally insecure. Right? So there are various risks here that the tokenization standard outlines, from guessing the secret data. So imagine you have a encryption-based tokenization algorithm. Someone would try to guess the key for that encryption, and you've got like someone trying to predict how you map the tokens to a pan. So you can imagine something like, if someone comes up with a real simple tokenization algorithm, it will be really easy to predict, okay, what's that pan going to translate into. Then there's, of course, authentication, authorization, all that part that you have to make sure that only those entities talk to the tokenization service that are actually allowed to and should be talking to the tokenization services, and that illegal access is locked appropriately. And then, of course, there's overall system health, that you have to make sure that nobody subverts your system in a way that they get access to, say, the user that the tokenization system is running under. So one of the hottest topics in all these discussions was really, okay, where can you actually run the tokenization operation? So the actual translation of the USV, the underlying sensitive value, to the token and vice versa. Where can you run the algorithm that does that, and where can you store your tokenization secret? And there was quite some different, I would say, or a variety of companies in that group, of course, with various interests. And one of the things that was really hard to convince people is to not require everything to run in hardware, right? Because if we think about nonstop and doing tokenization on nonstop, for instance, if you would ever always have to go out to some hardware box to request the tokenization in an online transaction processing environment, that would basically totally break your performance and not be feasible, just because it's not fast enough. You have the latency talking to an external box, as well as there's just, if you have to buy hardware in the size that you would need to support your tokenization needs, that's just a commercially typically prohibitive thing that you would have to do. And those were quite some hard discussions to also bringing the position from the nonstop world, where you really have this online transaction performance that you have to ensure, and to make sure that you are actually be able to run tokenization on trusted platforms like the nonstop locally. And we ended up basically at a point where the medium assurance level is sufficient for complying with the standard, which basically means that you can run the tokenization processing in software if you use P2PE, which you should be using anyhow, right? So if you're doing kind of your normal security, then the key is you can also run the tokenization system in software. That means on trusted platforms like Nonstop, locally on the system. So, and that was kind of the other point is, okay, how do you isolate the rest of the system from your tokenization system? And yeah, do you have to have a different box that you go to for tokenization, or can you kind of segregate it in a way with the means that the system provides? And yeah, the isolation in a Nonstop server based on the architecture, of course, of a basically message-based shared nothing architecture of the Nonstop, that's one of the possible isolation methods. So basically, we were talking about, if you abstract this for the Nonstop world, about can you actually implement tokenization in a compliant way or not, right? Because had there been the requirement to do everything in hardware, yeah, no Nonstop customer in the world would have been compliant any time, any place. So let's look at the acceptable tokenization techniques. And if we look at kind of the overall data protection topic, you've got the classic encryption, which is typically, that's where the attributes come in, not format preserving. And then you've got the tokenization, which is the protection of a underlying sensitive data element in a format preserving way. And there are four means of how you can do the tokenization in the tokenization standard defined, and those are static table driven tokenization, which is basically what Comforter is doing, what Voltage is doing. Then there's encryption based tokenization. That's what Voltage is doing with the FPE. So the former one, the static table driven one, was the SST tokenization. Then there's on-demand random assignment, which is the classic piece everything started with, basically having a database where you have your mapping stored of the underlying sensitive data element to the token. And that's what RSA did. Meanwhile, RSA, as you probably know, not longer in this business anymore, and that's typically also what the issue was or is with those classic tokenization systems, that as soon as you have a database, you have to synchronize, of course, that database of all your systems. You have constant I/O, and you have a huge growing database that you have to maintain. So basically that just doesn't scale, and for high performance systems that doesn't work. And yeah, that was also one of the reasons RSA got out of this. And then there's MAC-based tokenization, which probably I would wonder if anyone ever used. That was more of a, someone insisted to getting it in, and it's basically you can do a MAC-based tokenization in the sense that you hash your underlying sensitive data element. You cannot unhash it by design from tokenization or from regular hashing algorithms. It's a one-way operation, but you can basically do a similar operation to match. If you have, it's like passwords basically. So if you want to check a password at the provider side, you don't have to store the password, you store the hash of the password instead, and then you can match if the user inputs his or her password, then you hash it, compare it, and you know if that's the same. So that's the MAC-based tokenization. As I said, would make me wonder if anyone in real life would actually use this for something that's close to tokenization. So basically, nowadays, what you see a lot is static table-driven tokenization and encryption-based tokenization. And there's a lot of marketing fuss around the difference of tokenization and encryption. And as you see here in the tokenization standard, this encryption-based tokenization is part of the overall tokenization, as opposed to what some companies position it as, okay, we have encryption, so format-preserving encryption is something different than tokenization. If you see here, basically from the standards side, it's just one way of doing tokenization. And the point, maybe to add that as a background, is that there was some benefit for PCI scope reduction. When auditors saw, okay, you do tokenization, you would get your scope reduced if you have tokens on the system. If you do encryption, typically the system would be in scope. And that was kind of the reasoning behind, okay, the fuss about marketing tokenization versus encryption. Basically, even if you use encryption algorithms to conduct the tokenization, it's still tokenization, which meanwhile PCI has also kind of adjusted to and takes it as tokenization as opposed to encryption. So then let's look at the Annex C, and that's about the static table-driven tokenization reference schemes. And in that annex, basically it starts with, well, outlining the general approach, what is being done in static table-driven tokenization, and then it refers to the C2 and C3 sections for the actual ways how to do this. Then we've got in the C2, it's basically a way of doing tokenization basically on a direct table lookup, which is basically taking or storing all possible values that that the underlying sensitive data element can be in advance. And that, of course, only scales to a certain extent. So this is for like elements smaller than, if you tokenize smaller than 5 digits, then you can use that. But what's really the typical and future-proof algorithm there is the ones based on the Feistel network. And I'll spare you the details of how a Feistel network works, but basically it's a construction that has been used in various encryption algorithms and has been around for a long time, and has been incorporated in order to not only do encryption but design tokenization schemes around this. And that's what then the Annex C3 talks about. Basically outlines how this Feistel networks can be used to achieve tokenization, what security you have to put around it to achieve this, to do this in a secure way, and then ultimately talks about, okay, what are the what are reference functions that you can look at, how you should be doing something if you're designing a scheme, or if you are looking at a scheme that someone designed, how should that look from a security perspective and from a design perspective. And there are 2 reference algorithms in there. One is the voltage tokenization algorithm, which is this SST, and then the other one is the comforted tokenization algorithm, as then the one of the reference algorithms for static table-driven tokenization. So at the end of the tokenization standard, it's basically touching on use cases for tokenization, respectively tokenization guidance. And one of the things that it touches on is the whole topic of payment tokenization versus security tokenization. And the key here is basically what it says is, okay, payment tokenization produces tokens that still have some value that needs to be protected. So basically, depending on the value you have assigned to your payment tokens and what you can do with that, you might have to also protect them when you store them, when you use them. for instance, with security tokenization. So let's look at tokenization use cases. And well, the kind of easiest one and closest one is, of course, okay, well, you can tokenize your own data to secure your data, right? So, and that can be the merchant at the payment gateway, networks and issuers. So basically everyone storing sensitive data can tokenize that for his own purpose. That's kind of the trivial thing. What we've been seeing quite a bit recently is people actually doing something what I abbreviated with merchant out of scope, a use case where the payment gateway utilizes a tokenization system in order to, instead of handing out a pen to the merchant that's then being stored, handing out a token that's being stored. So basically, the payment gateway provides the service to hand out tokens to the merchant, which has the benefit that the scope of the merchant is getting reduced because they don't store any sensitive data elements anymore. And of course, they can settle against their payment gateway based on the tokens because, well, obviously the payment gateway is able to detokenize those tokens. And that's what we've seen, depending where you look on the world. In some parts, North America, we've been seeing some cases where the merchants actually went to their payment processor and said, well, if you cannot offer me such a service so that I can reduce my costs, I will just look for another service provider. Right? So this is really something of potentially losing customers if you don't have that added value. In other regions of the world, what I've been seeing in Asia, for instance, is that payment processors are looking, of course, for competitive advantage. So there's nobody being able to provide such a service yet. So they are looking in, okay, this can be added to our portfolio in the payment gateway to provide such a service as a value add for the merchant. So basically, the payment gateway has that as a value add charged service, and the merchant still saves money because they have a much smaller risk exposure and a much smaller PCI scope that they have to handle. So, and of course that can be also done as a service, or with an intermediary in the cloud. Same use case, but it's just the difference that it's not longer the payment gateway that actually provides that service, but a third party in the middle. Okay, so hope that was useful for you, and thank you a lot for your attendance.